All right, pre-calc. Next section. This section is just kind of talking about applications of vectors and how we can use them. And so this is part one. There's going to be two parts of this, and this can be a little bit tricky at times. So I'm going to ask you to really kind of try to use your brain and try to utilize logic and try to find out what we're trying to do with these problems. You're going to have to rely on some prior knowledge. So we know that we can use some vector addition, and we can also use trigonometry and a little geometry as well to solve vector problems that involve oblique triangles. So we're talking about triangles that are not right triangles. Okay, so that means you're probably going to need that you can use some parallel line info. Right, they're angles. I should say lines, angle info. You know, that's your alternate interior, alternate exterior, corresponding, all those. Okay, and then also law of sines and cosines for some of these triangles. So we can use those. We'll give you a sheet on that so you can kind of have a reminder on those things. All right, so let's get right into the problems and let's see what we can do. All right, this first problem, there's a lot that I don't like about the first problem, but we'll kind of get to it and talk about it there. So now we don't necessarily need the protractor and to get the exact angle and the exact scale as long as we can draw a picture of this thing. So let's work on drawing a picture and working from there. So we've got a farmer and his son are removing a large boulder from a well, and they're pulling ropes attached to the boulder. So the ropes make a 40-degree angle. If the farmer is pulling with a force of 115 newtons, that's what the N stands for, newtons, and his son is pulling with a force of 105 newtons, it's just a way of measuring force, then what is the magnitude and direction of the boulder? So we know we want to find magnitude and direction here. And so we're going to have kind of a two-part problem here, the net force on the boulder. So net force on the boulder means basically the resultant. It's going to be both of them added together. So let's draw a picture here and see how it works. So we've got our little boulder. Going to make a boulder here. Okay, and then we'll have our ropes that are attached to it. So let's say they form a little triangle, right? So I'm going to try to draw it big so we can see clearly. All right, so it says here that the ropes form a 40-degree angle. So that means that this angle here is going to be 40 degrees. Okay, this whole angle measure here is 40 degrees. Okay, but if we notice that, and I'm just going to draw this to be the farmer, and this is his son, okay? Their forces are a little bit different, right? So we've got, this is 115 newtons, and this is 105 newtons, okay? So together, they'll make a resultant force or a net force on the boulder. So for that, what we have to do is we kind of have to draw a little bit more here, because what we're going to notice is that with these vectors, they're pulling from the boulder and they're pulling in this direction. So this vector is going to be going that way, and this one is going to be going this way as well. When we think about adding these, we can't just go this way and get a resultant, because these are actually tail to tail. We start here and we start here going in that direction. So actually, what we're looking for now is we have to use the parallelogram method. Okay, so I'm going to have to do a parallelogram and just kind of sketch this piece over here now, and then this piece over here, right here, to kind of make a parallelogram. It's obviously not to scale, but it doesn't have to be when you're drawing. That's why we don't need to have the scale. We don't need to have the protractors here. So really what I'm looking for, remember, is looking for this value here, which is the resultant from here all the way down to here. That would be the measurement we're looking for. So that's what's in question. So if we call that, say, the resultant, or R, we'll use it as R, okay? In here, now we can kind of go about using some trigonometry for it. But we had to kind of figure that part out for. Now, again, we don't know that, we can't assume these are 20 and 20. We just know that the whole angle is 40 degrees. But because this is 115 and 105, they're not the same, then it's not exactly going to be 20 in one piece and 20 on the other. So all I know is that that side's 40, and because we have a parallelogram, that this whole side is 40. So what I'm left with is that this has to be 140, because to make a quadrilateral, we'd have to have 360. Or if we split it into triangles, regardless, we'd have 40, and this has to be 140. That helps us because this is the degree measure. Remember, when we use the law of cosines, which is what we're going to do, we're going to have r squared. That's what we're trying to find. And then we're going to use f squared, that's the farmer squared, plus s squared, that's the sun, and then minus 2 times f times the cosine of 140. Okay, why cosine of 140? Because that is the angle opposite of r. So remember, when we do law of cosines, whatever is over here, we use the angle opposite of that. So we're kind of plugging in those values. Okay, so really now what we're going to try to do is go r squared equals 115 squared plus 105 squared minus 2 times 115 times 105 times the cosine of 140. Okay, so now it's just calculating stuff. So the hardest part was kind of getting the picture drawn and getting the information that we needed, and now we're ready to go from there. Okay, so now I can just kind of punch that in my calculator, and then remember, take the square root at the end, and you're going to get r equal to about 206.76 newtons, and that acts as the magnitude, right? That's this whole thing here, because we're trying to find that side. It's basically finding the missing side of a triangle. Okay, now we had to use a quadrilateral to get this angle, knowing there's 140, and again, just knowing quadrilaterals add to 360, I've got 40 plus 40 is 80, so that means I need another 270, 140 here, 140 here, gives us those angles. Okay, so that's the magnitude. So that's the first part. All right, now here's where I really don't like the problem, if you didn't like it already. But when we talk about the direction, because direction, it doesn't tell us which angle we're looking for. Remember, direction is going to be an angle measure. So here we use law of cosines, but now we can use law of sines because now we have an extra measurement. We have this is 206.76. So really, we're going to use law of sines in conjunction with law of cosines to find the direction, but it doesn't tell us if we want the farmer's direction or the sun's direction. So again, it doesn't tell us if we want this angle or this angle, right? So let's just use, I guess, this first angle here. Okay, we'll call it angle A. So because it's 115, we know this is 105, right? Because opposite sides of a parallelogram have to be equal. So now I can go ahead and I can use law of sines here. And I can say, all right, the sine of A over A equals the sine of, well, we use R, I guess. We'll use sine of R over R because we already found that information out, right? We know that now. So now I can go, really, I can say the sine of A, that's what we're trying to find, over A, it's going to be the side opposite that, right? So here's A, side opposite that is 105. Because I'm just kind of focusing on this triangle here now, if I just kind of isolate this whole side, then that's what I'm going to kind of work on. So then the sine of R, I know that angle is 140. And I already found R to be this. Okay, so now when I cross multiply here and try to solve, basically you're going to end up with sine of A, just kind of speeding through some things after you cross multiply and solve. It's going to be 105 times the sine of 140, and we're going to divide that by 206.76. Okay, So you're going to end up getting, and remember, then you have to do the inverse side. So whatever you get here, remember trying to find an angle, so inverse it when you get here. So you should get angle A equals about 19.05. Now I skipped a couple steps there to get there, but 19.05 degrees. Okay, remember, because it can't be 20 and 20 because we have different forces coming across. So we couldn't just break this 40 into 20 and 20. So now we know that this is about 19.05, and I could find angle B now to be like 20.95 because they would have to add to 40. So if they were asking for both of them, I could get that for you at 20.95. Okay. So usually they'll tell you which angle you're looking for. That's one reason I don't like the problem. But in this case, we just kind of solved the triangle. Okay. So that's not as great of a problem. So I understand that. But again, using your brain to find the logic, get the picture down, then you're just using calculations and formulas we already know. Okay. So let's talk about this one now. The airplane flying with an airspeed of 310 knots. And this is on a heading. So that's what we call, it's like the direction the vessel is going is on a heading. And then we kind of steer it on there to overcome other forces. It's on a heading of 050. Okay. And then we've got the 78 knot wind blowing from, we'll talk about that as we go. And then it's blowing on a true heading of 125. And then we want the speed and direction. Okay. So we want speed and direction. So it's a similar problem than what we just did. Now this one, they tell us the plane relative to the ground. So they give us a little bit more action. All right, so let's start with a picture if we can. So let's look at the first part here. The airplane is flying with an airspeed of 310 knots and on a heading of 050. Okay, so when I do this, what I'm going to end up doing, I'm going to try to draw a line. I'm going to make this pretty large just to help us out here. I'm just going to make my y-axis here. Okay. And then I'm going to draw an x-axis right here just to help us with our drawing. Okay, so the first part, we got an airplane that's going at an airspeed of 310. Okay, so we'll draw our airplane. And it's at a angle of 50 degrees. Okay, so it's heading on a direction of 050. So we're assuming that's from the north, so we're going to go from here. And we're going out this direction, okay? And this is, say, 310 knots, right? That's what we looked at. Okay. And just remembering, just kind of drawing this in here, we've got, this is an angle from here of 50 degrees, okay? That right there is a 50-degree angle because that's what the headings told us, right here, right? Now, here's the next part. This is where it gets a little tricky on this one. It says a 78 knot wind is blowing from. That means it's going to point towards the x-axis. Just want to point that out. It's blowing from. It's going to point to the x-axis. Okay. A true heading of 125. Okay. If it would have said that it's a bearing of 125, then it would point away from the y-axis. But in this case, it says from. So again, I'm just going to point that out. From. So a true heading of 125. So that means we've got to point it to the y-axis. So just understand that from or at. Okay, in this case, it's from. So it means the wind is blowing towards the y-axis at 78. And this is at 125 degrees. Okay, so again, a true heading, meaning just coming from the north, right? When we don't have a direction, it means it comes from the north. All right, so this one here, I'm going to just kind of draw the angle this way from the north all the way down here. So this would be 90 right here, right? So I got to go a little bit more to make it 125. And I'm going to say that we'll do it in purple again. That this angle, 125, is that we're going this way here. That is the 78 knot wind. Okay. And again, remember that this here is 125 from the y-axis here. So that's a 125-degree angle there. Okay, so now we want to know the speed and direction of the plane relative to the ground. So basically the wind is blowing against the plane here. So to do this, I want to go tip to tail here because I've got my vector here. My plane is going off in this direction, but the wind is blowing back in this one. So if I want to go tip to tail here, I'm going to kind of take this vector here and I'm just going to translate it up to the top here. I'm just going to kind of move it from here to here. Okay, I'm going to translate it from there up there. Okay, so to do that, and again, this way I don't need to be exact because I just have to get the best I can to get on this angle here. I'm going in this direction here. So I just kind of translated that just like we did before in 8.1 when we kind of translated to add vectors. So now I'm actually looking at this one here that connects these two. That is the vector that I'm looking for. Okay, and since we're relative to the ground, we'll call it g. The velocity of that, we'll call that g. That's the one we don't know, and that's the one that we're trying to find. Okay, so this vector here is the one that we're trying to find out. So do I have enough information? Well, close, not quite though. So let's just draw on a couple different things that we need to remember. All right, now we know that this whole thing was 125 degrees, correct? Okay, well, that means, and we know that this angle here was 50, and this whole angle was 125. So I can find this little angle right in here, right here to be 75 degrees. Okay, I just take 125 minus 50, and that gives me 75 degrees. Okay, so that's that angle. And now here's where I have to use a little geometry. So because that angle is 75 degrees, this angle right here also has to be 75 degrees. And because parallel lines are cut by a transversal. Okay, so I'm just going to say remember those, because if this vector here that we drew here, the 310 knots, if that is a transversal cutting through parallel lines, like if I drew another line, we have the 75 degree angle here. So if I drew a parallel line, I'm just going to draw one really quick just to sketch it out here. If I drew one through this vector here, right, well, then we'd have another 75 because alternate interior angles, okay? So that means that's got to be the same there. All right, so now I have a little bit of information that I can use because now I've got the angle that's opposite. My G here is 75. So now I can go ahead and use law of cosines over here on the side. So I'm going to go ahead and do that. I've got enough information. I'm looking at, again, c squared equals a squared plus b squared minus 2ab times the cosine of c. That's the law of cosines. Okay. Well, really my c technically is g. So I'm looking at g squared equals, well, I've got a couple other values. I've got 78 right here squared plus I've got a 310 right here. So I've got the other value of the triangle. So I'm just trying to solve the triangle, find the missing values, which we've done before, which is getting the picture set up. Minus 2 times 78 times 310 times the cosine of, well, remember, it's going to be the angle opposite the side we're trying to find, cosine of 75. I wrote that. Okay, so again, now I can actually input that all in my calculator, and then I end up getting, so G is going to be the square root of all of that stuff. Okay, so I can actually punch this in my calculator. Just be careful with how you're punching it in, and then I'll end up getting G equal to about 299.4. So that tells me the speed here of this aircraft is 299.4. Okay, so that's the first part. That gave us the speed of that resultant vector. All right, now here's where I can use law of sines to find the other angle. Now they want the angle the direction of the plane relative to the ground. So really what they're looking for here is they kind of want this angle in here. We'll call that theta. That's the angle we want. So we have to do a couple things. They're looking for this angle right here from that vector from the true north direction. So they want that angle, remember, because it's the direction from the north. So they want this here. Well, so we have a couple of those things, but we don't have everything that we need. So really what I'm trying to find here is I'd like to find this angle right in here, angle A, this part of the triangle, okay? Because I have 75 and I have 78 knots and I have 299. I've got enough information to use law of sines. So let's go for it in green here. So I'm going to go sine of angle A over A equals sine of angle C over C. That's just the law of sines. So if angle A is right here in the triangle, right, the triangle that we formed, then it's going to be sine of A, that's what we're trying to find, over the side opposite that, which is the 78 knots. Stay with me here. And sine of C, I know, is the 75 degrees that we have here over this value that we just found, 299.4, or yeah, 299.4, okay? And then I can cross multiply and I can solve for the sine of A, okay? Remember, when I do this again, sine of A then is going to be equal to 78 times sine of 75 over 299.4. But again, don't forget, because you're trying to find an angle, you have to inverse assign this, all that stuff. And when I do that, I'm going to end up with A equals about 14.6 degrees. Okay. Now, we're not done, though, because that is angle A. Okay. That's angle A. We want theta in here. We want theta. So to do that, I know that this whole thing is 50. I know that angle A is 14.6. So really, theta is going to be 50 minus 14.6. So you have to look and see what we're trying to get. So that would equal 35.4 degrees. Okay, because remember, this is what we're trying to find, is this angle here. We know that this is 50. If we subtract A, that'll give us that value. So a little extra step there. That's why I said you got to use your brain, see what they're trying to find. Okay, let's move on to the next one. This one's a little bit simpler as far as drawing the picture. So Mitchell swims due east at a speed of 3.5 per second and goes across a river directly towards the opposite bank. At the same time, the current of the river is carrying him due south at a rate of 2 feet per second. So then we want speed and direction here. All right. So if I draw an axis here, that's, just that, let's say that's the shore. In this case, what's happening in this case is he was going 3.5 due east. So that's directly east. So we're going this way, straight east. This helps out because we don't have to worry about the angles. Okay. So that takes care of this part here. Going due east at a speed of 3.5. So if we just mark here that that's 3.5. Okay. And we're saying feet per second, right? Okay. At the same time, it says the current is taking him due south at a rate of 2 feet. So we go down here at 2 feet, and that's going to be 2 feet per second. Okay, so now you can see this kind of makes it a little simpler here when we're trying to find this vector right here, okay? Right there from the shore. And that's the vector we're looking at going this direction, okay? So trying to find speed, we can see that when we do that, we've got enough information. We know that this is a 90-degree angle, so that helps us, okay? So I could use actually trig. I'm going to go ahead and use the law of cosines just to get more practice with it, because I think you could use some trig and Pythagorean theorem if you wanted to, but I'm going to go ahead and do it this way, just so we practice law of cosines a little bit more, because of x squared, because that's what we're trying to find here, right, is x, we'll call it x. X squared equals a squared plus b squared minus 2ab times the cosine of capital X, right? So I can put those values in. So really it's x squared equals 3.5 squared plus 2 squared minus 2 times 3.5 times 2 times the cosine of 90, right? Because that's going to be the angle opposite x. That's why with a right triangle, you could actually use Pythagorean theorem and some other values if you didn't want to do this. I'm just showing you it still works with cosine, okay? So I'm going to end up square rooting all that, punch all that in, take the square root of it, and you're going to end up with about 4.03 feet per second. Okay, so that takes care of the speed. It's 4.03 feet per second. Okay, now they want the direction, right? So the direction is relative to the shore. Well, this is the shore over here. This is where we started. That's the shore. So when we talk about the angle, we're looking at this angle right here. That's the angle we want to find. So that, we'll call that theta. That's the angle we want to find, okay? So in order to do that, we're going to have to use the triangle. So if we call this, say, angle B, then we can use law of sines, because now we have some information. We know this is 4.03, okay? So now I can go ahead and use law of sines here, and I can say sine of B, because I need to use this triangle, so I have to find this angle first. Then I can subtract to get theta over 2 equals the sine of 90 over 4.03. And then using law of sines, I can end up, just kind of cross multiplying, solving there again. I'm going to end up with angle B equal to 29.75. Okay, but that's right here, right? 29.75. Okay, and then I also know that this whole measurement from here is a 90-degree angle. So to find theta, theta is going to be 90 minus the 29.75 just to get this angle here, which then is 60.25 degrees. Okay, because they tell you it's relative to the shore. So you have to kind of find that angle. All right, good. Moving on. Last one, last part, and this part's the easiest part. So we kind of got easier as we went. All right. So a couple things here first to mention, though, is that if we talk about vectors, 2 or more vectors with a sum, that is, say, vector R, those are called components of R. Okay, components of R. And while components have any direction, it's often useful to express or resolve a vector into 2 perpendicular components. These are called rectangular components, and they are the horizontal and vertical vectors that make up the resultant. Okay, so you look at this example, you've got R is the force here. That's the resultant of basically X plus Y, right? So X is the horizontal, Y is the vertical vector. So we see that X is the force that moves it vertically, and Y is the one that moves it horizontally. That makes R. So we can kind of use those, and this kind of gets easier because now you're just trying to find a vertical or horizontal marking. So if we look at the soccer ball example here, we could say you get the 44 foot vector, but I could say that this has the upward force and this is the horizontal force. So I could have my X and Y there, right? Simple as that. So for this one, draw a diagram that shows the resolution, this force into rectangular components. So all I'm doing there is I've got my 44 foot vector, okay, at 44 feet per second, and I know it's a 33-degree angle, so I'm just going to make this is X and this is Y. That's part A. Okay, that's part A right here. That's all I have to do. And I just have to draw in my angle. Okay, and I know that it was 33. It told me, it gave me the picture. I'm just kind of copying that down into triangle form. That's it. That's all you have to do there. If there's not a picture, if it just gives you words, try to do it that way. All right, letter B says, find the magnitude of the horizontal and vertical components of the velocity. All right, so they basically want the magnitude of this, X and Y. So in this case, we can kind of just use trigonometry because it's horizontal, so I know it's a right triangle here. So I can use some trig formulas. And in this case for X, right, if I use my SOHCAHTOA stuff, my SOHCAHTOA rules, I've got, here's the angle we're talking about. X is the adjacent angle, and then this is the hypotenuse, right? So I could say the cosine, we're talking adjacent and hypotenuse. So cosine of 33 degrees would equal the adjacent side X over the hypotenuse of 44. And we just know that it's got to be positive because we're talking about magnitude. And so to find this, the magnitude would equal 44 times the cosine of 33. So the magnitude of X would be about 36.90 feet per second. Okay, for Y, same thing here. Y, if we're talking about this angle 33 degrees, Y is the opposite side, and we still have the hypotenuse for 44. So in that case, opposite over hypotenuse, I'm going to use sine. So sine of 33 degrees equals the magnitude of Y over 44. So continuing on there, it would be 44 times the sine of 33, just doing some math, and then the magnitude of Y then is equal to about 23.96 feet per second. Okay, so buckle up. We've got some problems to work on. Draw the pictures, see how you can figure it out. We'll help you along the way, but this is how we can use trig and some geometry, law of sines, law of cosines, to help out with vector addition, or with solving these problems with hopefully triangles.